the intrinsic concentration. Can we determine the number of electrons and the number of number of ores in a given volume, or in other words, what we call concentration? So we remember, whenever we dope a material, this, what we are saying are the majority carriers are donated for N type. They are donated by donor atoms. For P type, they are donated by, we get these ores from acceptor atoms. So we use that approximation. In P type, almost all the ores are coming from the acceptor atoms. In N type, almost all the electrons are coming from the donor atoms. And we did that for this question. Okay, since we are given donor concentration, we say the number of electrons is equal to the number of donor atoms, which we are given the number of atoms per centimeter cubed. Then once we get that, we can now say, okay, we want P. If we want P, we look at the where there is N, we substitute with ND in this equation. This one, where there is N, we substitute with N subscript D, which is the donor concentration, and that's what we have done here. And that enables us to get the concentration of ores. So you should, we assume you are able to use the mass action law correctly to determine the concentration of either ores or electrons. So now when we look at the P type and N type on their own, a material which is P type is not very useful. A material which is N type on its own is not very useful. So what we do, we will look at now combining them. If we combine or we fuse together P type and N type, what do we get? So we get, look, I bring a N type and a P type. I fuse them together, and this one brings so let's go back to this. Look at this. This is the P region, the N region. So the boundary between the P region and the N region, we call it PN junction. And there's something which happens when you bring the P region where we have ores, the ores cross into the N region because of attraction. The electrons in the N region cross to the area with the ores. So what do we have remaining around the junction? When this acceptor atom loses a hole, it becomes an ion, a negative ion. When this donor atom loses an electron, it becomes an ion, which is positive. So we have positive ions and negative ions. Now those who are joining later, making our work difficult. So we have this, what we are as the small circle with a negative unit site is a negative acceptor atom. I will repeat again how this negative acceptor atom is formed. We have the acceptor atoms having O's and the O's cross. So what remains is a negative ion. When an acceptor atom loses a all, it becomes a negative ion. When a donor atom loses an electron, it becomes a positive ion. So this region near the junction contains ions. Therefore, we say it doesn't contain charge carriers, and we call it depletion layer. So the terminologies we are using, you must get used to them. We have the PN junction. Why do we call it PN? Because we have the P region and the N region when we fuse together these two materials. And in this area around the PN junction, we have recombination of charge carriers, electrons cross or cross. So around the junction, we remain with ions, and ions don't move. Ions cannot move, and we say this region does not have charge carriers, and the reason we call it, that's the reason we call it depletion. And it is now behaving like a capacitor with one side here being positive and this one being negative. So the positive side of the depletion layer has a higher potential. We can show that it has a higher potential, and that makes our what we call potential gradient. So this side, which is negative, has a lower potential. That's why we draw this. And it is showing the potential difference across the junction. So if this side is behaving like positive, then we have an electrical field. We have an electrical field which is having a direction from positive to negative. So this is the direction of the electric field in the depletion layer. Now, if you understand these two diagrams, then you will have no problem understanding the rest of the discussion. And I think I sent this this slide to you.
Nobody bad.
Now, those who are making noise, just don't disturb others. So Nelson, we remove you from the class. I'm just making noise for us. Nelson, we must remove you from this class. Please don't come in again. Please, unless I ask you to speak, don't speak. And there's no need of coming to class when so Nelson, you will have to answer during the physical class why you are disturbing us. So please don't join this class again. Get back to our discussion. And I think I'm not allowing any other student who is coming late. So we have said we have a potential difference, and we also should realize there's something else happening. As we move from the end region towards the PN junction, the number of charge carriers reduce. And also on the other side, therefore, we are going to talk of this having a higher density of charge carriers than this. Therefore, we can have what we call diffusion. And we are also having a potential gradient. So two things which you must pay attention to. And I think that this is the most difficult part of this course, understanding what happens in the PN junction. So there is a potential difference. There is diffusion taking place. Because of the potential difference, we can have current being forced to go through because of the electric field. So we can also have a situation where we connect. When you look at this, there is nothing, we have not connected any external source of voltage. So we say this PN junction is unbiased. Now, if we connect an external source of voltage or EMF to the PN junction, such that we have the positive of the external connected to P and the negative of the external connected to N, we say the PN junction is forward biased. So what is the situation? We have this positive side of the external source will push us to go to this side. And this negative will push electrons to go to this side. And in effect, we have the depletion layer becoming very small in a way that the electrons can cross and the ores can cross. And when we have ores crossing, they get attracted by the negative of the external source. Electrons which have crossed get attracted to the positive of the external source, and therefore we have a flow of electrons and ores. I repeat, if you are in this class, you must remain muted. We notice somebody disturbing others, we will have to throw him out of the class. So here, when a PN junction is forward biased, there is conduction of current. When it is reverse biased, the situation looks like this. The situation looks like this. We have the positive of the external source connected to the end region, the P region connected to negative side. So what happens, the ores are attracted to this side, or electrons are attracted to this side, and therefore the depletion region widens. When we have forward biasing, the depletion layer is very narrow, and that's why electrons and ores can cross. So here we don't have any charge carriers crossing the depletion layer. Therefore, there is no conduction. So a PN junction does not conduct when it is reverse biased. Neither, if we continue increasing the biasing voltage, we widen the depletion layer much more. we widen the depletion layer much more, and that actually, if it continues, it can destroy the PN junction. Now I want to hear from the class rep, Okoth. You can hear me? Okoth?
Yeah, I can hear you.
No, I sent you some of this. I sent you this set of slides, is it?
The ones for lesson 5 and lesson 6.
No, what did I send to you?
Okay, let me check.
Means you don't know. Okay, just this is one of what I sent to you, and here we repeat what we have just said. Reverse biased PN junction, there is no conduction. A forward biased PN junction conducts, there is electron flow. This one is unbiased. We have not connected any external EMF. Therefore, there is just what happens, which we said in this slide. We just have holes and electrons crossing for a very short time to create the depletion layer, and that process stops. And that's why we don't have current flowing here. We have current flowing here. We don't have current flowing. The reason why we don't have current flowing here is because of reverse bias. Here there is no external power. So this makes the PN junction a special device that it can only conduct current when it is forward biased. When it is reverse biased, it behaves like a poor conductor of electricity. And that's why we'll see later one application of the PN junction is making a device we call diode, which conducts electricity in one direction. A resistor, we know resistor can conduct in both directions. Diode conducts only in one direction. And here in this section, we want to explain how this is possible, the transport of carriers. And this transport is of the carriers are either ores or electrons. And we said there is in the PN junction, whether biased or unbiased, there is an electric field across the depletion layer. And there is also variation of concentration. I will take you back to where I was explaining that. Here we said there is, as you approach the junction, the density of electrons decreases. Density of ores as you approach the PN junction decreases. So there is variation of concentration of charge, and therefore you can have diffusion. What is diffusion from chemistry? Remember, diffusion is movement of particles from area of high concentration to area of lower concentration. There's also the electric field, which can affect flow of charge, and that is exactly what we are saying here. Charge can flow either due to the electric field, and we call that current which flows due to electric field, we call it drift current. And the current which flows due to variation of concentration, we call it diffusion current. So we will spend some time looking at carrier transport. What causes charge to flow. There are only two ways: the electric field or the variation of concentration of charge carriers. So we will see the associated mathematics, and I think class rep, you do mathematics, is it? This class, you are taking mathematics?
Yes.
So you understand the integration, you understand differentiation, okay, and you also understand from your the physics you did in secondary school, the what we call velocity. We know that velocity is distance divided by time, and therefore distance will be equal to velocity times time. Look at this. We want to define something we call drift velocity, and we start from the very basics we learned in secondary school, that velocity is distance divided by time, and therefore distance will be equal to velocity times change in time. So we are looking at a material and we feel a small part which we call a small length of that material, which we are calling delta x. So if a charge crosses this area, it will have crossed a distance delta x. So we are looking at just one charge, one particle whose charge is q. So it is crossing from this side to this side. And what is the distance it travels? It is v delta t. And in practice, charge carriers don't move in a straight line. They actually move in a zigzag manner. Again, if you remember in secondary school, you were taught something known as Brownian motion, which you are taught is zigzag in manner. So if we understand this, and then it is the beginning of wisdom. Look, we have said delta x is v multiplied by delta t. Delta means change. A small change of distance will be given by Vd, and Vd is what we call drift velocity. So we want to come up with an equation where we can have measurable parameters. We may not be able to measure this small change. We may not be able to, so we want to express the drift velocity using measurable quantities. So we start from here. Then if this is the length, let us look again at this diagram. If I want the volume of this small element, I will multiply the cross-section area A with the height of this small cylinder, which we are saying is delta x. So we have a small element whose cross-section area is A and its length is delta x. The volume of that small element is area times delta x, and we know delta x is v d delta t. So to get the volume of this small cylinder, I will multiply v delta t, I multiply with a, and that is where we are having this. And of course, in a given volume, we know the concentration of the material. The concentration we say is either small p or small n, if I'm looking at electrons. So the number of carriers in that small element of the material is n. because N is the number of carriers per unit volume. And the volume we have said is A, where is the cross-section area, multiplied by V, which is the velocity we are calling drift velocity, and delta T is the change in time. So this equation 5.2 give us the number of carriers. If we know the number of carriers in a unit volume and we know the volume, then we can get the number of carriers. I hope you understand. So let me just use the class rep. Of course, you understand equation 5.2? Of course.
Yes.
Do you understand how we have obtained equation 5.2?
No.
Oh, yeah. And do you know how to get volume of a cylinder?
Yes.
How do you get volume of a cylinder? If you know the area of the cross section, how will you get the volume? Yes, cylinder. Yeah.
Squared H.
A squared. A is the area, the cross section area. So you can't say A squared. H. A is the cross section area. So the volume will be in the language you're used to. So the base area times the height gives us the volume, and we know the height is V delta T. So this is the height, and A, the cross-section area. Therefore, the volume will be V delta TA. And if we ask ourselves how many carriers are in that small volume, we will multiply the concentration of carriers with the volume. And that is exactly what we have in equation 5.2. So we have, this in brackets is the number of charge carriers, and each charge has a charge Q. Therefore, the total charge in that small cross-section area is NAV delta TQ. What is Q? I take you back here. Q is the charge on one carrier. So I told you this is, I try to make it as simple as possible. Then we remember from basic physics that current is given by the rate of charge and the rate of flow of charge. That is delta Q multiplied by, divided by delta T. That gives you current. I repeat, we define current as the rate of charge flow. So we take our equation now 5.3 and divide it by delta T, because this is what gives us the what? The delta Q. Look, delta Q is here. So if I divide it by delta T, I get current, because we are saying current is delta Q divided by delta T. That is the, if you see here, when we divide this equation, I think you can see when we divide by delta T, this cancels out and we remain with NAVQ. That's what we have here. N A V Q. That is the current. So we can use we can try to answer this question. Okoth, can you read for me this example? Can you read? And I ask you if you have a notebook somewhere with you. You write down equation 5.3. Okoth, can you read this example?
Yeah. So power in a typical residential building has a cross-sectional area of 3.31 times 10 raised to the power negative 6 meters squared and 8.94 times 10 28 electrons meter cubed. If it carries a current of 10 amperes, what is the drift speed of the electrons?
So we are given the cross-section area as 3.3, and we are also given the concentration of electrons in that small element of material we are considering. So this is a copper wire, has a cross-section area of this and this number of electrons in a given volume. And there is a current flowing through which is 10. So what do we want? We want then drift velocity. So we use equation 5.3. We are given the current. We are given the concentration of the electrons. We know Q. Q is not. I think if you remember again your elementary physics, Q is as a value 1.6 times 10 raised to power negative 19. So we are required to get V. So we make V the subject. So we'll be having V equals to I divided by N Q A. Do we know the value of A? Yes, it is this one. Do we know the value of N? 1.6 times 10 raised to power negative 9. Do we know the value of A? Yes, it's here. Therefore, that equation 5.3 becomes this. V equals to I divided by NQA. So we put our I is 10 amperes. Our N is 8.49 times 10 raised to power 28 per meter cubed. And the Q is 1.6 times 10 raised to power negative 19. A is 3.31 times 10 raised to power negative 6 meters squared. And this one, if you work out, you will find it, you get 2.22 times 10 raised to power negative. You must confuse yourself because already you have these notes. You should cross-check what we are doing. Determine for yourself, is this correct?
Excuse me.
Yes?
Excuse me, sir.
Yes?
I didn't receive the note. I did not receive the notes.
No, I think I even have the message which you replied to. I asked you whether you have received, and you said yes.
Oh yeah, the previous ones I had received them. There were 2 documents.
Check that. Please check that email. You will find these ones there.
Okay.
And share with your friends. This is quite important. If you did you tell your classmates you are writing card number 1 next week?
Yeah.
Yes. So you must. I just this particular one I sent to you because I know it's a bit challenging. Actually, I sent 2 sets of slides in that last email. Okay, so we have answered that question. The question was, what is the drift speed of the electrons, and that drift is quite small. It looks very small. That is what happens in the atomic world. So we can also define something we call current density. How much current is in a given area. So current density is defined by equation 5.4, and it is I divided by A. It's just like if when we go to class in OML 8, we can calculate the density of students in that class by looking at the number of students and divide by the area of the class. It will tell us in a unit area, there are so many students. So in a unit area of a conductor, can we determine what we call current density? We'll take the current flowing and divide by the cross-section area of the semiconductor. And of course, if we go back to equation 5.3, if I take it to 5.3, which is here, if I divide this equation by A to get current density, I'll remain with NQV. NQV. So I don't know whether you can still agree with me. You are doing introduction to electronics. So that is the one form of the current. We are able to, sorry, we are able to relate current and velocity, drift velocity, charge carry and density. And now we can look at what we said is drift current. There are two types of currents in a PN junction: drift current and diffusion current. Drift current is caused by the difference in electric field or difference in voltage, that is potential difference. So on drift velocity, sorry, drift current, we have to look at this the drift current we say it is caused by the difference caused by the electric field. Diffusion current caused by differential concentration. We gave those definitions here. Drift current is associated with electric current and diffusion current. So we will try and again look at the mathematical derivations to enable us to